All right, this is going to be a screencast on the free body diagrams worksheet that has to do with Newton's laws. And I'm going to use this for review and for grading. I'm going to use red since we're grading this. And we're going to start with letter A. And it says, a physics book rests upon a level table. So we're going to draw our box. And with all of these problems, almost every time you're going to have the force of gravity acting upon it. So you're going to draw a force vector downward, and you're going to label that F grav. And then on the way up, you're going to have the normal force. And since the book is not moving, it's resting, the vectors need to be equal to show a balanced force. And this force is called the normal force. So we're going to call it F norm. And if you look at what the F norm is here, it says when an object is sitting on a level surface, then the normal force is always equal and opposite to the weight of the object. So that's where we're always going to get this balanced force vector. There's no forces right or left, so we're finished with that one. We'll move on to B. And a skydiver is falling and has reached a terminal velocity. So we're going to draw our skydiver. And once again, we start with gravity. So we're going to have F grav. Then they're at terminal velocity, which means that they are no longer accelerating. And since they are no longer accelerating, we know that the forces acting on the skydiver need to be equal and opposite in both directions. Because if this gravity was greater, they would be accelerating downward. And if this vector was greater, they would be slowing down, but they're not. They're traveling at a constant speed. And since the skydiver is going to have a lot of air resistance pushing back on them, we're going to call that F air. Letter C. A large crate is being pushed leftward at a constant velocity. So we have our crate. And once again, a crate has gravity applied to it. And we just talked about this. So if there must be an equal and opposite when it's on a surface pressing back up on the crate because it's a balanced force. And that's going to be the normal force again. And the crate is moving to the left. It's being pushed left. So we know we have to have a force pushing it left, and that's going to be applied to it. So that's going to be an F ap. And it's moving at a constant velocity. So there's no acceleration. So we need to make sure that these two lines are the same in length, representing the magnitude of the force. And this, when you're pushing a crate along the ground, you're going to have a lot of friction. So that's that one. D is a sledder has reached the bottom of a hill and is coasting rightward while slowing down. So we have a sledder. Once again, gravity is pushing down on this sledder. And we have the normal force pressing back up. And the sledder is coasting rightward. But remember, when something is coasting, it's just using its inertia. So there is no more applied force. That was already done when the sledder was running and jumping on the sled. So the only force that is now there is the force that opposes motion, which we know that as friction. And this is saying that there is going to be an acceleration to the left, in this case a deceleration or a slowing down. So that would be it for that one. All right, that moves us to letter E. And a ball is moving upward towards its peak. Ignore air resistance. So we have the ball. And once again, we have good old gravity pressing down. By the way, gravity on Earth, the force of it, things are always accelerated at 9.8 meters per second squared on Earth. And that's something you'll need to know. Remember, meters per second squared is the unit for acceleration. Now the ball has been thrown upward, and you need to ignore air resistance. So it's running off of inertia again. The force has already been applied. So there's no more forces acting upon the ball. It's going to be, when you throw it up in the air, it's going to be slowing down, which this is represented here with this acceleration, which we call a deceleration of gravity. And the ball is going to be slowing down, finally come to a stop, and then fall back down to Earth. An air track glider moves rightward at a constant speed. This one, since we're not totally sure what an air track glider is, let's not grade this one. Just count it right no matter what you put. But just for one thing you would definitely have no matter what would be F grav again. And since it's not moving up or down, we're going to have a balanced force pressing back on it. And that's the normal force. And you could call it finished there. You could all argue that there is a little bit of friction keeping it from moving rightward. And in that case, there would be a little bit of friction to the left if you wanted to put that. But since an air track glider has very little friction, you could assume that there's none. G, the brakes are applied to a rightward moving car as it skids to a stop. So we got our car here. Once again, gravity is on the car, and the ground is pushing equal and opposite back up on it. So we have our normal force again. And it's moving rightward, coming to a stop. But once you take your foot off the accelerator, you no longer are applying any force. So it's just in its coast mode, running off inertia. So the only thing now slowing it down is the force that opposes motion, which is friction. And we have a deceleration or an acceleration here, negative acceleration, slowing it down. A spider is slowly descending on a thin silk thread at a constant speed. So we got our spider. Gravity affects a spider, even though it's very, very light. It still does. And we now, since it's going at a constant speed, we have no acceleration, which means these forces have to be balanced. So we just have to determine what this force upward to balance it is. And a spider thread is going to be under tension. So we're going to call that F10. S, I think they use TENS. All right. Moves us on to I, which is an elevator. Is rising at a constant velocity. It is not touching the elevator shaft. So we have our elevator. It's rising at a constant velocity, but let's start off with what we know is there for sure, which is gravity pulling it down. And there is an equal and opposite force pulling it back up because it's going at a constant velocity. And so this force would be tension. Now, it didn't tell you to ignore air resistance. So if you wanted to, this is fine if you just have this. But there would be a slight amount of air resistance opposing its motion upward, which would be F air. And the thing you would have to realize here is if you did add that in, which you don't have to, this force vector along with this force vector, right, that would be known additionally down here. So we would have to lengthen the length of this just a little bit so that these lines would all be balanced and equal. HI. Okay, so I skipped I. Sorry about that. That was J. So let's go back now and do I. So this one is letter I. And we have a projectile is moving upwards and rightwards towards its peak of its trajectory. So we have a projectile, and we know that gravity will want to pull it back down to Earth. And the applied forces have already